My name is Kamyab Zandi. I work at Chalmers University of Technology at the Division of Structural Engineering, a concrete structure research group. The university is located in Gothenburg, Sweden. But I also work at CBI, the Swedish Cement and Concrete Research Institute, which is located in a small city about 60 kilometers outside Gothenburg, which is called Borås. So in this webinar, we're going to be looking into a little bit about research and some practical application when it comes to simulation-aided damage assessment in reinforced concrete structures. But before I get into the topic, I would like to share with you some of the research areas that we work with, both at CBI and at Chalmers. So we work a lot with material modeling, this fundamental theory work of a material modeling. We work with dynamic response with XFEM. We work with the non-local models, specifically localization and compression. We work with cyclic loading, and very much for a long time we've been working with different bond models describing the interaction between concrete and reinforcement. And from there we started to develop, to expand the model to different deterioration mechanisms such as corrosion that we're going to be talking about in this webinar. We also work a lot with the finite element structural analysis for design and evaluation. So we run analysis for full-scale structures like bridge. We do also work with model updating using field measurements, and also we use finite element structural analysis to evaluate the safety of infrastructures. Another area of interest for our research is impact loading. So we work a lot with different aspects when it comes to civil defense shelters, with fragment impact, projectile impact on plain and reinforced concrete. We work with dynamic response in the structures, strain rate effects, and blast and fragment loading effect of reinforcement. In particular at CBI, we also work with flow analysis of fresh concrete. We look into discrete approach using computational fluid dynamics, CFD, to look at the flow of fresh concrete. And we also work with continuous approach using the distinct element method. And the practical application of these methods is actually the fact that we work with simulation of self-compacting concrete for on-site casting. We also work with simulations for novel material and reinforcement. So we work with test and simulation at the material level, like this example for a wedge splitting test. We work with specimens in different environments, such as in corrosive environment, and look into the fact that how corrosion penetrates or chloride penetrates through the concrete cover, and when such a specimen is loaded, how the crack widths and crack distribution is influenced. We'll look into steel fiber reinforced concrete, and we'll look into different material properties of this material, and also we work with textile reinforced concrete. And lastly, we work with also simulation-aided damage assessment in concrete structures. In particular, we have been working for a long time with the modeling of the swelling effect of corrosion. We have been also working with multi-scale modeling of coupled chloride moisture diffusion. I would say corrosion is what we really been working for a long time with, but we also work with frost damage, with sulphate attack, and with ASR. So now, from now on, I'm going to be focused on the simulation-aided damage assessment in concrete structures. In terms of the people or the colleague who works on this topic, it's myself. The figure to the left, I'm privileged to work both at CBI and Chalmers. I'm leading this research group working with modeling and simulation techniques. Then we have Karin Lundgren, professor at Chalmers. She leads concrete structures research group. Mario Plos, who is the leader of the Division of Structural Engineering. We have Mohammad Tahir Shamsi at Chalmers, who works with natural corrosion and also tries to calibrate our model with respect to natural corrosion. And we have Gabriel Jansson at CBI, who works with different aspects of assessment in reinforced concrete structures. And having this collaboration between research institute and university actually enabled us to start from the science of our work at the university and try to take that into application at CBI, and then from there we really try to push that forward to international committees and try to bring the best of our work, the findings of our work, into standards. But why do we bother a lot about our existing structures? This is a very nice bridge, a beautiful one, close to Stockholm. It's called Skrubron, built in 1915. If you manage to go beneath the bridge and have a look at some of the beams, what you find out is that there has been corrosion going on for a long time, and it has not only led to cracking but also covers falling. So with naked eyes you can really see the reinforcement and the rust on the surface. So the question is, what is the impact of this type of deterioration on our society in general? We think that there's a huge economical impact because the value of the built environment, at least in Europe, is about 50% of the national wealth, and it's extremely important to have an optimized maintenance and rehabs, and simulation and modeling is one of the ways that can help us to come to this optimization. We also would like to reduce the environmental impact, so we have to really take care of our existing infrastructure, trying to use them as long as possible, as long as they are still safe to use. And we would like also to meet the future challenges. One important thing is that now we know that the climate change actually will accelerate the deterioration rate, so we have to be really prepared for that. Thus, really having these computational models helping to predict different aspects of service life of existing structures is really important. So by that, I finished the introduction to this webinar, but from now on I'm going to be talking a little bit about a strategy for simulation-aided assessment. I'll be talking about deterioration models, but I will be only focused on corrosion, even though I will later on give examples regarding sulphate attack, but I'm not going into details of the model. I will just show the results. So it's the corrosion part, the corrosion model, that I will discuss quite in detail. Then in terms of practical application of our research finding, I would like to share with you two examples. First of all, how we use these computational models at detail level to answer some of the frequently asked questions regarding bridge structures when they are influenced by corrosion. And the second example has to do with the application of our model, where we studied harbour structure piles affected by sulphate attack. So let's just start from this strategy that we try to follow when we do simulation-aided assessments. We believe that whenever it comes to assessment, you have to really be prepared to look into different methods and to look into different scales. So we call it multi-method, multi-scale approach, where we try to have an estimation or try to test material and the structure. So we start from material and structural testing. But then we have to combine that with different monitoring techniques for damage. When the damage is going on the structure, or when you actually test specimens taken from reality. So in this case we use digital image correlation to look at the strain localization. We also use acoustic emission to capture where the most fracture in our specimen takes place. We also look into microscopical analysis, try to understand what is the mechanism that triggers the damage in the first place. That helps if you want to prevent your damage. That helps a lot, but also to understand how the damage influences the structural behavior. You have to have an understanding of the mechanism itself. And when we get a little bit of understanding of different parts here, then we come to modeling and simulation. So that's actually the very last part that we add in our investigation, because then we know a little bit about material, a little bit about the damage mechanism and so on, and then we can choose proper inputs for our models. looking into different scales in this approach, it's quite important to realize that deteriorations actually start at the small scales, meaning that you have to have an understanding of what happens at the scale of aggregate cement here in this figure. And then from there you try actually to estimate, for instance, the chloride ingress through the concrete cover and so on. In a larger scale, we'll look into material properties of plain concrete. In this case, we're looking into a wedge splitting test, how corrosion induced crack is opened up in a wedge splitting test. Then we go to a scale higher up where we have a full bearing element. In this case, this is a beam, but that's the first time we look into a reinforced concrete. So we have the reinforcement included in the analysis. And it's actually a very detailed analysis, I would say. Then we go to a higher scale where we look into the entire infrastructure. That's where we look at the load-bearing capacity and possibly the service life of your structure. And if you manage to go all the way through these scales, then that's where we can talk a little bit about the life cycle of your structure. You can say that, well, this is the service life that we estimate, and then you can look at pros and cons of in terms of prolonging the service life. It's possible and see if that has any economical impacts, any environmental impacts, and so on. So starting from the smaller scale, we look at the cement and aggregates and the interface between cement and aggregates, and we do multi-scale modeling of coupled chloride moisture diffusion. And that's, as I said, we start with deterioration modeling. In the material model, it's actually the fracture properties of the plain concrete we look into, and we could also look into fiber reinforced concrete. In this scale, we'll actually look into reinforcement and how, for instance, corrosion of reinforcement may influence the load-bearing capacity. This is a structural analysis of a full-scale structure, and at the end, that enables a life cycle analysis of your infrastructure. So that was a quite short review of the strategy we try to adopt. So we look into different scales and we look into different methods. And we really try to couple simulations and modeling with experiments at different scales. So let's have a look at two practical applications. Well, before I come to the application, I would like to start looking into different deterioration models, but in this case in particular with corrosion models. The first question is that how corrosion may influence the structural behavior. If you have a corrosion problem, so you know that either you have uniform corrosion or pitting corrosion or both at the same time, but any type of corrosion you may have that leads to a volume expansion around the reinforcement, and that may lead to cracking in concrete, and if the cracks are really wide open, that may lead to covers falling. So you have a reduction in the cross-section area of your element, meaning that you may have influence on the moment capacity, shear capacity, but also on the anchorage capacity. Thus, you have a concern about the load-bearing or the load-carrying capacity of your structure, and also the stiffness and force redistribution in your structure. But uniform and pitting corrosion may also influence the rebar properties itself. So you have a little bit of change in the ductility of reinforcement, but also the cross-section of the reinforcement is changed, meaning that you have the change in the capacity of your structure and the stiffness and force redistribution. But we have been working quite a lot on the anchorage capacity in particular, because that's the most difficult, most challenging task when you deal with corrosion. And one of the important things when you talk about anchorage, one of the important parameters is how the interaction between reinforcement and concrete is triggered. Now here we are looking at reinforcement, reinforcement. When you try to pull it out, when you have a force on the reinforcement, you have the concrete around it, meaning that you have pressure on the ribs, and that gives you two forces, radial and normal forces on the reinforcement. The model we have been trying to develop has actually two aspects. It's actually, it has a yield line which describes an upper limit for a pull-out failure based on the stress in the inclined compressive struts. And also we look at the friction between the reinforcement and concrete and try to regulate how how friction can describe the interaction, and also how corrosion may influence this friction model. What we do in the model is that we actually have implemented the swelling effect of a corrosion product into a subroutine which is coupled with our structural analysis that we carry out with Diana. What are the most important parameters when you try to run such analysis is how the material properties of corrosion products is. It's really important to have an estimation of your of the material properties of rust. So in this case we have been trying to look at different experiments and trying to run analysis and see what is it that best describes properties of rust. And what we have come to back in 2002 was that actually rust is a granular material, meaning that when you put pressure on it in the beginning, it takes the pressure, it has a lot of deformation, but later on the stress, with a little bit higher strain, the stress really raises up, which means that we are dealing with the granular material. So that was the first time ever mechanical properties of rust has been estimated for this type of analysis. But later on in 2005 and also in 2013 there has been experimentations and also simulations approving or verifying the granular behavior of rust. The model works in a way that we have formulated this swelling effect in an interface element between the reinforcement and concrete in Diana. So what we have here, it's a concrete specimens with the reinforcement and then this interface element in between the reinforcement and concrete describing the bond and the corrosion in terms of swelling effects. The specimens is the ones that has been tested by Al-Musallam. And now we are looking at some of the results. Here we are looking at the force, the pull-out force on the reinforcement, and on the horizontal axis we are looking at the corrosion penetration. And what you see, the blue line corresponds to the experimental findings, where we have a little bit of higher bond capacity or anchorage capacity in the beginning when we have small amounts of corrosion penetration, because actually before cracking you expect to have a little bit higher bond because you have a higher confinement due to expansion of corrosion. But as soon as you have cracking, then the force or the bond drops very rapidly. How rapid this drop is, that depends on how much confinement you have in terms of concrete and transverse reinforcements. What we got from our simulations based on the model that I just described is that we start from by having a very good agreement in the beginning, but we did not include this positive impact of swelling effect of corrosion for low amount of corrosion. So we go with a straight line here, but as soon as we get to a cracking point, then we actually capture this rapid drop in the pull-out force. So the model has been verified with very many different specimens, and that's one of those verifications. Another aspect that we have been trying to implement in our model is the impact of rust flowing through the cracks. What happens is that As soon as you have the swelling effect of corrosion getting to a level where you have high stresses, you get cracking. And that cracking is a release of stresses locally around the cracks, but also it has an effect because it allows for the rust to flow out. And this has a good impact, because as much if you allow for the rust to escape from the surrounding of reinforcement, that means that you built up less pressure. So we wanted to implement that in our model. So we did both simulations and experiments for the sake of verification. Our specimen, actually we had 3 different type of specimens. We looked into beam end specimen. We call it eccentric pull-out test, where we have a specimen type A, where we have only bottom reinforcement exposed to corrosion, and we have no stirrups along the embedment lengths. Specimen type B, we have 4 stirrups along the embedment lengths, but the stirrups were not subjected to corrosion. And type C, we have the same specimen, but this time the stirrups were also exposed to corrosion. So we ran the analysis. We ran the experiments in 2 phases. The first phase was artificial corrosion, trying to subject the reinforcement to corrosion, and then after that we pull out the reinforcement. Either we pull out 2 corner bars or 1 middle bar in the tests. So we did 3D nonlinear structural analysis quite at detail level. We had, of course, concrete model with solid elements, but also all the reinforcement in these specimens were included with solid elements. We also had the interface elements between the reinforcement and concrete, and in the shaded areas, that's where we have the corrosion model also imposed in the model. So now at the figure to the right, we look at 1 stirrups and look at 1 main reinforcement, and the shaded area where the reinforcement were subjected to corrosion in the lab, and that's exactly how we try to implement that in the simulations. Starting from the original model, if you think about a reinforcement located at the corner of a section, we start from a non-corroded bar with a radius of r, then we have the corrosion penetration, and what happens is that we have the expansion around the reinforcement, and since we have the concrete around the reinforcement, that gives a little bit of pressure on this rust, but at the end we have the cracking. So we try to reformulate this, starting from the same condition when we have the corrosion penetration, the expansion of corrosion product, but this time, as soon as we have the cracking, then we allow for the rust to flow out. So we calculate how is flowing out by actually measuring the crack widths in the simulation. And then we still have the concrete around the reinforcement, meaning that we still have some pressure on the rust, so we have a little bit of the compaction there as well. We implemented that as a subroutine in our Diana analysis. So we locally get the crack widths from the analysis, and similar to what we do in molecular dynamics analysis, we probe a single molecule of rust movement in the crack. So we do exactly the same through Newtonian formulation. With that, we estimate what is the volume of rust which manages to flow out through the crack. So we're looking at some of the results of this model. Now we are looking at the corrosion phase. Here we have the crack width, and here we have the corrosion weight loss in percentage. In blue we have the corner bar, and in red we have the middle bar. So these are the values of corrosion, so 7.3% of corrosion weight loss. And looking at the experimental results, this is how the crack widths develop for different amount of corrosion. Of course, we have a point here at 0, and then we jump over here and continue. And if we look at the response or the findings of the model before we include the flow of rust, this is what we get. So we have we well estimate the crack widths in the beginning, but then we continue with quite a straight line because we do not allow for the rust to flow out in the analysis. But as soon as we move to the extended model, where we include we account for the rust flowing out through the cracks, then we see this behavior that in the beginning we have crack widths growing very fast, but after a while allowing for rust to flow out, then we have slower crack width growth, and that corresponds well with the experiments. And if we look at the middle bar, we see pretty much the same behavior, that in the beginning we have a high rate for crack widths development, and then it slows down, and that's what we get in the analysis, where we also include the impact of rust flowing out through the cracks. We look at some of the crack patterns. On the top we have the crack pattern sketch from the test in the lab. So here is the specimen type A without any stirrups, where we see that we have actually we have more local crack pattern. In this case we have corner covers falling. That's what also we see in the simulations. In type B, where we have stirrups also included, then cracks actually take in a form that they tend to end up with the cover delamination. So one crack here, and then that propagates to the middle bar and so on. And that's what we also see in the simulations. And where we have also the stirrups exposed to corrosion, where we have very diffused crack pattern, it's very difficult to capture that in the simulation. But actually we see that in the simulation we have cracks where we have the corroding stirrups. And to some extent that corresponds to what we see in the lab on the experiments. Now moving into the pull-out tests phase. Now we are looking at the average bond stress versus free-end slip. So we pull out each of these reinforcements, we measure the slip on the back, and then we measure the force in front, and we show here bond stress versus free-end slip. Now looking at the non-corroded case, so from experiment and from analysis, and then for the corroded reinforcement, this is for the middle bar, and then this is for the corner bar. So we have quite good agreement between what we can estimate by 3D analysis and what we see in the experiments. Looking at some of the crack patterns coming from simulations. On the top we have reference specimens with no corrosion imposed, and on the bottom we have corroded specimens. And we see that corrosion highly influenced the crack pattern. Here we have more of a corner covers fall. When you pull out the reinforcement down here, we have the corner covers falling, but also we have the interaction between corner reinforcement and middle reinforcement. And then when we move towards the case where we have stirrups corroding, then it's more of a bottom cover delamination case, and that is very well shown in the simulations. Then the third aspect that we wanted to implement in our simulations, was that what happens if we go far into corrosion and then we get into covers falling, because in simulations we always have a problem as soon as we get to high crack width. So starting from the original model, we just take into account the swelling effect of corrosion product. If we look at this schematic description illustration for the relation between bond strength and corrosion penetration, as we saw earlier, we start with this part in the beginning where we have a little bit of higher bond capacity. We do not take that into account in our simulation, but as soon as we get to cracking, then we have a sharp drop in the bond strengths. And we think that if we use the original corrosion model, we can capture what happens around the first cracking, but it's hard to move any further because we get to large crack widths and we come into numerical problems. So when we added this effect with rust flowing out through the cracks, we managed to go a little bit further in the analysis. Now we can go for higher corrosion penetration, and coming to a case where we look at lower bond strength values. But still we cannot go all the way, because at one point the cracks would be so large and the cracks will be connected all to each other, and we come to a delamination plane, and that cannot be described with regular finite element analysis. So what we do is that actually we have written a script in MATLAB which is coupled to Diana now. What we do is that we actually in each step of analysis we take out the stresses and the strains from Diana. We bring that into our MATLAB code, MATLAB script, and we look into the crack widths pattern and whether or not the crack has been joined together to develop a delamination plane. And if that is not the case, then we go back to the simulation and continue. But if that is the case, if we have large crack widths and if we have formed a delamination plane, then we go actually to Diana. We go back to the analysis environment in Diana, but in this case then we deactivate all the elements which belong to the spalling part. As you see in this figure, all these elements down on the bottom, they all correspond to the delamination plane. And then we go back to the Diana environment and then deactivate all these elements and continue. Having this computational scheme, what happens is that now we manage to go even further, because as soon as we have large crack widths and we have covered delamination, just before we run into numerical problems, we deactivate the elements. And that allows us to go for larger corrosion penetration, meaning that we go for higher swelling effects of corrosion products. And we have actually validated that with quite a few specimens, which I'm not showing here. But saying that we have validated that, the important question is how we use such a complicated model in practical application. Because it's really computationally very expensive to run these type of simulations. It's a matter of weeks or months to run analysis for specimens of about half a meter in length, for example. So there has to be a way that we use this model to better understand what happens in reality, and then start with simple models. So here I would like to bring forward a few practical applications that based on this model we try to implement. So the first question that we try to answer with this model is that imagine a case where you have the main reinforcement exposed to corrosion. What happens is that you have the expansion around the main reinforcement, and if you have stirrups very close to the main reinforcement, then you get some stresses in the stirrups. And usually stirrups are there to help you with the shear stresses. But what happens when you already have some stresses in the stirrups induced due to corrosion of the main bar? So in this case, we try to look at a cross-section. This is half a cross-section. We have one reinforcement on the top, one reinforcement on the bottom in the corner, and one reinforcement at the middle of the section, and we have one stirrups all around it. So we try to impose corrosion on these two bars on the bottom, and then study the stresses on the stirrups. So down in this curve, what you see is a stress in the stirrups, and here is along the stirrups. So what you see is that here we have this main reinforcement corroding, and that imposes some stresses on the stirrups. So in this case, we are looking at different level of corrosion for the main reinforcement from 2% to about 20%. So what we see is that for about 20% of corrosion on the main bar, we have about 50 megapascal of stresses in the stirrups, and that means that you have less available stresses to be taken due to shear, right? But we also try to understand is this so important? This 50 MPa of induced stresses in the syrups, what that means. So if we look into about 20% corrosion in main bar, that induces stresses in the syrup, in this case about 80 MPa, which is about 15% of the yield strength of your syrup, right? But what if we look at a case where we have 20% of corrosion on the main bar, and then you have your syrup there, and that is translated to about 25% corrosion on the syrups, and that means you are losing about 25% of the cross section, or you have to decrease the yield strength of your syrups by about 25%. And in addition to that, you get early cracking due to corrosion of syrups. You get early cover spalling due to corrosion of syrups, and on top of everything else, you have this notch effect due to pitting corrosion in case you have a pitting corrosion. Putting all these together and comparing these two cases, we get an impression that even though corrosion of a main bar induces some stresses in the syrups, but that is not as important as corrosion in the syrups directly. So that was then we formulate actually recommendations in our guidelines based on these findings. That's more important to look into whether or not you have corrosion on the syrups rather than how much stresses you have on the syrups due to the expansion, due to the corrosion on the main bar. But it's also important to realize that maybe you get quite high stresses on the syrups. In this case, it's about 80 megapascal, but as soon as you go away from the location of the main bar, then these stresses really go down nearly to zero. So you rapidly diminish within a short distance when you go away from the corroded main bar. And that is important to know, because then you have only concern about the case where a shear crack crosses right at the bend of the reinforcement where you have highest stresses. Another question is that to what extent will the corrosion of a syrup influence actually the cracking pattern and the time to cracking? So we use this 3D detail model to look at different cases, to look at these specimens. Now we have type A, type 1, type 2, and type 3, the same thing as I described before. Now we are looking at bond strength versus corrosion weight loss. What we see is that in type A, where we have no stirrups, then we actually drop the bond strength very rapidly for even very small corrosion penetration, and then we continue with the same capacity, with the same strength. But in case where we have stirrups included, then we start from a higher point. But the difference between type 2 and type 3 is that in type 3 we have also the stirrups corroding. And what happens is that in that case then you have a sharp drop in the beginning and then continue. But if you do not have any corrosion on the stirrups, then you actually maintain a little bit higher bond strength for low corrosion penetration. That means that the impact of your stirrups being exposed to corrosion is that you get a lot earlier cracking and maybe earlier spalling, but the very final capacity is not influenced by the corrosion of stirrups if you do not get yielding in stirrups. So this is another practical application of the model we've developed. And then the third question is that we might not have always uniform corrosion. So usually we get corrosion on one side, half of a bar or 1/4 of a bar. Like in this case in our specimens, if you have sharp eyes here, you see that on the left side we have had corrosion, but nothing on the right side. So we try to actually run our model for different corrosion distribution around the main bar, and what we see is that doesn't actually influence the bond strength at all in this case, in this geometry that we were looking into. as long as you stick to the same amount of corrosion weight loss, not corrosion penetration, but what happens is that it doesn't matter if you really have it on one side of the bar, not on the other side, or not all around it. If you manage to measure the corrosion weight loss, you can actually ignore how it is distributed because it will not influence the bond strength at all in this case. So now I'm done with this frequently asked question that we try to use the corrosion model and bring up some answers to them. Now we are moving to a case study where we looked into at a few piles taken from a harbor structure, and we tried to identify what was the dominant deterioration mechanism. In this case it was sulphate attack. We will come to it in a minute. And then we tried to use simulations to better understand the bearing capacity of these piles. But I'm not going to describe how we actually implemented the impact of sulphate attack in our simulations, but I can just give you a hint that it was very similar to the way that we worked with the corrosion model. In the corrosion model we have this swelling effect at the interface between reinforcement and concrete, and in case of sulphate attack we have pretty much the same thing. So we actually impose this expansion within the cement paste or where we have actually the sulphate attack. So let's begin with this little case study. It was about mechanical behavior of concrete piles affected by external sulphate attack. It was me involved in this project together with colleagues from SP, the Technical Research Institute of Sweden, colleagues from CBI, and also colleagues from the harbour, the owner of the harbour. The harbour we're talking about is in Gothenburg at the beautiful river of Gota Älv. If you look at what happens beneath the surface of the river, we have the river stream with fresh water on the top, then we have the salted water on the bottom. Since salted water is actually heavier, so that's really on the lower levels, but then in some parts in the middle we have actually piles which are exposed to both fresh water and salt water. In fact, the external sulphate attack has been identified in inspections of quays and piers. There has been a need for better understanding of the connection between sulphate attack and the mechanical behavior of the concrete in order to schedule repair and strengthening work. We also were aiming at a better basis for assessment of the remaining service life and load-bearing capacity of these piles. So what we did was that we had a chance to bring two piles to the lab. One of them, which we call them pile A, were damaged to had mild damage on it. It was no severe damage, but then pile B was severely damaged due to sulphate attack. We started by this multi-scale, multi-method approach. So we used material and structural testing in terms of quantifying the compressive strengths or the behavior of concrete in compression and in tension. We also did full-scale test on some of the piles. We used digital image correlation and acoustic imaging to look at the strain localization on the surface of these piles where they were tested, and also we used acoustic imaging to see where we have the highest fracture activity to better understand the failure mechanisms. And then we also used microscopical analysis to better quantify the impact of sulphate attack in terms of how much expansion do we have. So we counted the cracks, we calculated the crack widths in a representative volume, and from there we actually calculated how much expansion we have had in this specific case. And at the end we did numerical analysis full columns, knowing how much expansion we have and how the expansion is distributed across the cross-section, and then running full-scale analysis on that. A little bit about the preparation of the piles. So we brought them to the lab. We cut one part of the pile for the stub pile as a stub pile specimens for the full-scale testing, but the rest of the pile was used to core out a few cylinders, and then for those cylinders we looked into, we tried to put them under compression, in tension, and try to understand the behavior of concrete in tension and compression. We also used the same specimens for macroscopical analysis to understand how much expansion we have had due to sulphate attack in these cases. What we got from macroscopical analysis was that we had actually the diffusion of sulfide ions into the cement paste, but it was not all across the cross section. So we had more impact of this expansion at the surface and less when we moved into the cross section, and that was a formation of Eccentric and the expansion of cement paste. In terms of the behavior of concrete in compression, we did compressive test. We look at the modulus of elasticity. We actually got the entire stress-strain response of these specimens, and we tried to use digital image correlation in a very innovative way to identify how the stiffness of concrete is changing in the concrete cover. We also use acoustic emission to evaluate the damage. So the acoustic emission and digital image correlation were used together to understand the distribution of the damage across the cross section. We did, as I said, we did also a direct tensile test to look at to have a value for the strength, but also having a stress crack opening relation, which is an direct input to our analysis, and we also looked into the fracture properties. So down here in this table we have pile A, mildly damaged one, with the elastic modulus on average about 30 gigapascal, compressive strength of 52 MPa, tensile strength of 3.2, and fracture energy of 187. And then down here we have so I move forward to the next slide here. So as I mentioned, we try to look at the stiffness of this damaged concrete starting from the surface of the column or surface of the cross section to more deeper part of the cross section. So here we are looking at the surface down to about 80 millimeter, and we were looking at this by digital image correlation and acoustic emission while we're putting these cores in compression. So what you see here is that in case of pile A, which was mildly damaged, we had more dense structure at the surface of the cross section, meaning that we have a little bit of higher stiffness in that area. And for pile B with severely damaged, for the severely damaged case, we had a porous structure. And then we saw that we have less stiffness closer to the surface. And that means that we had quite precise inputs for our analysis. We actually, in our analysis, we divided the concrete cover into different layers, and then we assigned different stiffness, different material properties to these layers. This is just some results from acoustic emission for pile A and pile B, and what we see is that, well, that's why we were actually putting these piles in compression, and what we saw was that we had a lot more fracture activity going on for pile A, and that was because the reason was that it was not damaged, so we had to develop the cracks while we were putting that under mechanical loading. While in severely damaged case, many cracks have had developed before, so there was less fracture activity going on, but it was more about opening up the existing cracks. So we tried to use a finite element model for these columns or for these piles. We actually, in the lab, we broke down the specimens after testing to identify what type of reinforcement we have and what is the reinforcement configuration, and we tried to mimic exactly the same configuration in our model. So we actually use the embedded reinforcement in this case for reinforcement. And then for concrete properties, we directly use the results from compression test in our analysis. Actually, what you see here on the right, we have the compressive stress versus compressive strain. And for pile A, which was mildly damaged, what we see is that the Thornfold curve very much corresponds to what we also saw in these columns. But for pile B, which was severely damaged, then we see that the application of Thornfold curve for compression behavior is not a good option. So we actually use exactly the same stress strain curve that we got from the experiments. So we also thought that it's important to try to induce the pre-existing crack or pre-existing cracks in our model. So we looked at only a thin section of the piles in our model and try to use our corrosion model, but this time to have the swelling effect due to sulphate attack. So it was actually the expansion was taking place in the cement paste. It was not around the reinforcement. And then we tried to check the crack pattern we got from the simulations in comparison to what we looked at or what we have in the piles through microscopy analysis. So what you see is that in the microscopy analysis we saw cracking like in this direction and then all the way from this reinforcement to this and then down here. And that's what we also see, that due to expansion of sulphate attack, what we see is that we have cracking all the way to the reinforcement, to the corner, and all the way to the other side of the cross section. We tested the piles in the lab with the displacement control regime with a rate of 0.3 millimeter per minute. And the results in terms of the load and deformation for pile A and pile B. Here we have the experimental results, and then here we have with the circles we have the simulation results. As we expected, we actually managed to capture the response with quite good agreement for mildly damaged one. When it came to the severely damaged pile, it was less agreement, but at least we managed to capture quite well the stiffness in the beginning. And then I would also say that the load-bearing capacity of the pile was well estimated, but not the deformation at the failure. So the concluding remarks were we had reasonable agreement between the analysis and the experiment, and we managed also to look into the failure modes, combining simulations with digital image correlation and acoustic emission. So by that, I would like to finish this presentation. I would like to thank you, Maziar, and all colleagues at TNO. Here I have a few slides for the references if you need to have a little bit more information with respect to these analyses, the fundamentals of the models, and the practical application. You can look into some of these references. Thank you very much. Back to you, Maziar.